This is just a little discussion of the graphs associated with our uniform acceleration model so that we can see how they give rise to the mathematical relationships we'll be using. Just as a starting point, let's first consider this graph of circumference versus diameter. Remember that the slope of this graph is the value pi, and because the general equation for a line is y equals mx plus b, the graph yields the equation circumference equals pi times diameter. Similarly, this graph has a slope which also has a meaning. Here we have the position x versus the time t, and the slope we assign the meaning of the average velocity v bar. We get the relationship delta x equals v bar times delta t by substituting the variables we have into the general equation for a line y equals mx plus b. In this graph, we have a position time graph which isn't a line, it's a curve. And so we can see that the object at point A is moving slowly, and it gets faster and faster as it proceeds from points A to B, C, D, and E. And we can tell this because the steepness of the curve increases with time. What I've done here is draw little tangent lines to the curve at points A, B, C, D, and E. A tangent is a line that intersects the curve only at one point. So you can imagine that at the tangents, or the slopes of those tangents correspond to the velocity of the object at points A, B, C, D, and E. If we had a way to find the slopes of those tangents, we would know the instantaneous velocity of the object. This slide is here to remind us about the distinction between the average velocity for a time interval and the instantaneous velocity at any point during the time interval. So the slope of the indicated line would give us the average velocity, v bar, for the whole interval, but the object is probably only moving at that velocity somewhere around point C. You see that the tangent line at point C is more or less parallel to the average velocity for the whole interval. So earlier than C, the object is moving slower than average, and then after C, the object is moving faster than the average velocity. If we had a way to find the slopes of those tangent lines, what we could do is we could find the time associated with points A, B, C, D, and E, and then we could find the slopes of the tangent lines associated with points A, B, C, D, and E, and we can put them in a nice little bitty table like this one. Then we could make a graph of the slope, which would be the instantaneous velocity versus time. If the object was moving with uniform acceleration, as you learned in your freshman course, you would get a velocity time graph that's a straight diagonal line. That means that the velocity is changing by the same amount with each successive time interval. Another thing that's useful to remember from your freshman course is that the area under the VT graph has a meaning. So here I tried to draw an object moving at a constant speed of 2 meters per second for 4 seconds. And I tried to draw like little boxes below that, each box being 1 meter per second tall and 1 second wide. So you can see that there are 8 boxes in there that would be corresponding to the area of the rectangle 2 meters per second by 4 seconds. And when you multiply 2 meters per second times 4 seconds, voila, you get a value of 8 meters. And that's the displacement of this object for the 4-second interval. We could still find the displacement for an object that isn't moving at constant speed. Here we have a velocity time graph with a line that is a straight diagonal line. If we happen to know the formula for the area of a triangle, we could calculate the area under this graph shown in red. Now if you look at the Excel file that accompanied this video, you'll notice that the velocity time graph that I plotted out has a slope of 95.58 centimeters per second per second. That's the acceleration of the cart. The position versus time squared graph has a straight line as well, and the value of that slope is 47.16 centimeters per second squared. Notice that those two values, the 95.58 of the acceleration is about twice that of the x versus t squared graph. So if that's the case, then the slope of our xt graph has a new meaning. It's 1/2 of a. So that gives us the equation of this line as delta x equals 1/2 a times delta t squared. That is our first equation, which relates the position, the acceleration, and the time all in one package. And that's the cornerstone of the rest of our analysis of uniform acceleration. So if that's the case, then the displacement of the triangle here also has a value of 1/2 a delta t squared. So here we have a new situation. This is a velocity time graph. The object starts with an initial velocity v0, and then the graph goes up in a straight diagonal line. Consider that the area I have in hatch marks there is a rectangle, and the rectangle has a height of v0 and a base of t. So since this is a velocity time graph and the area is equal to displacement, the displacement of that rectangle is equal to v0 times delta t. So now we can apply our previous analysis and claim that the area of this triangle is equal to 1/2 a times delta t squared. So the total displacement of that figure is the area of the rectangle plus the area of the triangle. The area of the rectangle has a displacement of v0 times delta t, and the area of the triangle has a displacement of 1/2 a delta t squared. And so the whole thing, the whole displacement, is v0 delta t plus 1/2 a delta t squared. We can unpack that delta x and give us the relationship x equals x0 plus v0 delta t plus 1/2 a delta t squared. And that's the golden equation you'll find in many textbooks.